Hello. Okay, here we go. Work. What's the definition of work? My definition of work is really simple. Work is energy happening. So if something has energy in it and you use that energy to actually do something, that something that gets done is the work. Um, just as a kind of a conceptual example, let's say you've got a bowl of soup or cereal or something, and it's got, let's say, 100 joules worth of energy in it. If you eat that soup or cereal or whatever, it goes into you, and so now you can use that energy to do work. Work like climbing upstairs, maybe, or building something, or making something. So, work is energy happening. So, if you've looked ahead here, you've seen that it says force times distance here, F times d. If you're going to do work, something has to get moved some distance. So you've got to move something some number of meters, or a fraction of a meter. So what's force? That's going to be newtons. So work is newtons times meters. So let's write that here in our units, N times M. So what does that tell us? Well, we know that newtons, that's force, and force is mass times acceleration by Newton's second law. So what we have really is we've got mass times acceleration. So let me write this again. Mass is kilograms, acceleration is meters per second, or you could say meters per second squared, times this other meters here. So if we do that, we get kilogram meters squared per second squared. This is the unit of work. Now, nobody really wants to write this. This is a hassle. So what we did was we picked a very famous, very smart dead guy, and we said we're going to say that unit is actually called the joule, named after James Joule, who studied energy and work. So there you go. The unit of work and energy are both joules. So let's skip ahead to what some people consider to be a trick question. Let's say we've got a big tree, and let's say you walk up to it and you push on it. You apply a force to that tree, and you spend some time pushing on the tree, and it moves a distance of 0 meters. It doesn't move at all. Hey, it's a big tree. So if this number right here, if this distance is a 0, then that means that the work is 0. Because in work equals force times distance, if the distance is 0, any number times 0 is 0. So does that explain why at the end of the day your muscles are all sore and tired? Well, work was done, but the work that was done was on your tissues, on your muscles and bones and stuff, not on the tree. So if you don't move something, then no work is done. Another example. Let's say we've got a box sitting on the floor, and we're going to pick that box up. Let's say it's a 2-kilogram box. That's our mass. And later on, we've taken that box and we're holding it up over our heads. And what have we done? Have we done work to it? Well, we applied a force. We moved it a distance. So yes, we did do some work. Let's say it's a height of, let's say we moved it up 2 meters. So we've got a distance, we've got a mass, so we've got an M number and a kilogram number. But what about our force? What force did we have to do? Well, what force did we fight against to lift this box up? We fought against the force of gravity. That was the acceleration that we fought against. And on Earth, our gravity is an acceleration of 9.8 meters per second per second. So if we want to figure out how much work was done, we've got to do work equals force times distance. And the force, like we said earlier, force is mass times acceleration. And then that's just multiplied by the distance. So there you go. Work equals mad. So some people get mad when they do work. Bad joke. Anyway, so we've got 2 kilograms. I'm going to leave the units off here. Our acceleration was 9.8 meters per second, and the distance we lifted it was 2 meters. So 9.8 is pretty close to 10. 10 times 2 is 20. 20 times 2 is 40. So we did about 40 joules, a little bit less than 40 joules of work to lift that box up over our head. So if we wrote this equation right here, if we wrote this a different way, the distance is a height, and the acceleration is gravity, and the mass is still just a mass. M times G times H, that is the equation for potential energy. That should make sense to you, because this box on the ground here, if that has a height of 0, it has no potential energy, and when you raise it up 2 meters, it's got that much more potential energy. So when you lift the box up, the potential energy that you gave it is the work that you did to lift it that high. The same thing works for kinetic energy. Let's say we've got an object, ooh, that's not very good, but let's say we've got an object sliding sideways. Let's say we've got a 5 kilogram box sliding sideways at 3 meters per second. And we want to stop that box. We're going to try and slow it down. I'll just draw a little person here, like he's going to try and stop the box. So how do we figure out how much work he does to get that velocity down to 0? He's going to try and slow it down to 0. Well, the work that he does, he's going to change the kinetic energy. He's going to take the kinetic energy of the box down to 0. So kinetic energy was mass times velocity squared over 2. So the mass of this box was 5. The velocity was 3. That gets squared, don't forget. So 3 squared is 9. 9 times 5 is 45. 45 divided by 2 is, what's that, 22 and a half? So this box that's sliding along, it has this many joules worth of kinetic energy. And if we want to do work on that box and stop it, we have to do that much work. So the amount of work is 22.5 joules. Now, so hopefully you see that there is a relationship between potential energy, kinetic energy, and work. As you change the amount of energy, then work must be done. So speaking of changing the amount of energy, let me finish this video with one last example of a kind of a trick question that I've seen before. Let's say we've got a box on the floor, and this person is going to pick the box up, and they're going to carry it over here. So we're going to draw this person again, and now they've got the box over here. Well, when they take this box and when they pick it up, we've already established that yes, they do work when they pick it up because we solved a problem like that. But when they walk the box over here, when they walk over this way, do they do any work? Well, think about that for a second. Does the height of the box change from here to here? No, it doesn't. It's the same height. So we didn't give it any potential energy. But did we change its kinetic energy? Well, when we picked it up here, it wasn't moving, and during the walk, it was moving. So we must have done some work to it, just not very much. All we had to do was fight against a little bit of friction in the floor for us to move sideways. And so the answer is it's very close to 0 joules worth of work because we did the real work in picking the box up, not in moving it sideways. Now, if the amount of friction in the floor becomes significant, then that number wouldn't be 0. But watch for the wording of the questions on work and energy problems.